Hi Year 12. What we're going to do is just finish off your mechanics unit basically, instead of trying to start the next unit on pure, which is differentiation, which is something that we haven't seen before. I want to teach us that in person basically. So we're going to just finish off these questions on pulleys. So it's connected particles, but these are changed a little bit. Now the reason that these change a little bit is that instead of now having two things that are both sort of on a surface and being pulled in one direction, if you think about it, when they're like this, if I pull this one in this direction, this one moves in this direction, and that sounds dead easy. If however the two things rest over a pulley like this, what happens to this particle here? If I call these A and B, just consider what happens to particle B if I pull particle A down. Which direction does particle B move in if I pull particle A down? Well, if that side moves down, that side moves up, which means that we cannot model this as a whole system. We must consider the particles separately and then try and link them together. Okay. Now, when you kind of get used to this will seem like a lot of work in a second, but when you get used to it, these questions I think are easier than the ones that you've already done. But once you get used to them, okay. So just remember about that. Again, light inextensible string. The reason it's light, we don't have to consider its weight. Inextensible means acceleration is constant throughout the string, and a smooth pulley. This means that the pulley being smooth means there's no friction, which means that tension is the same right the way through. You think about it, if there was something up here, if this was like a rough surface, as I pull that down, that would start to create more friction up here for the actual string itself, which would mean that tension would change depending on which side of the pulley you would be on. Okay, so smooth pulley means no friction, therefore tension is the same throughout the system. Okay, so first you need to be able to do with these is draw a diagram, so we're always going to start off with that part first. Right, particles P and Q of masses 2m and 3m are attached to the ends of a light inextensible string. String passes over a small smooth fixed pulley and the masses hang with the string taut. The system is released from rest. So before we go on to the questions, let's draw that out. There's my pulley, okay, there's my string down to mass P, which is 2m, and there's my string down to mass Q, which is 3m. Okay, so that's generally what these always look like. So let's put the forces onto this diagram then. The force here, the weight, will act downwards, and that will be 2 mg. The weight there will act downwards, that will be 3 mg. Tension, remember, always acts away from the mass. So tension will act there and there. It will also act here and here. Okay. And also it's important to show which direction the system is going to move in for both particles. On this side, this is the heavier weight, isn't it? 3m must be bigger than 2m. So that side is going to go down with that acceleration. This side will move up with the same acceleration. Right? So that's all the forces marked in the diagram there. So part AI, write down an equation of motion for P. Now when you get used to these, you'll be able to do this just by looking at this, but what I'm going to do is I'm going to draw out P. Now notice what I'll do here. P is 2m and the forces are 2mg acting down and T acting up. Effectively what you do when you just consider one particle is you block out everything else past the T. Okay, so all I'm looking at are the forces acting directly on that particle. This does have an effect on this, however that is represented effectively in that T arrow there going up. So all the other complexities involved in the system are basically shown by that arrow there. So you don't need to consider anything else apart from those, the T acting up, the 2mg acting down, and the fact that this thing goes up that way. So we can now write down an equation of motion. Remember, that's F equals ma. So in terms of the forces, what's pulling it in the direction of motion? Tension is. What's opposing motion? 2mg, the weight, and that will equal the mass, which is 2m times the acceleration, which is a. Okay, right, AII asks for the same thing for the other particle. So if you want to pause the video and have a go at that, you can do. Stop it now because I'm going to talk about it now. So I'm going to do exactly the same thing. I'm going to draw this out, and I'm only going to mark on tension and the weight because they're the only things directly acting on that particle, and this particle, remember, is travelling downwards with the acceleration. So again, F equals ma. What is pulling it in the direction of motion? Well, the weight is pulling it down, isn't it? So that's 3mg. What's opposing motion here? The tension, which is pulling it back up, and that will equal the mass, which is 3m times a. So those are my two equations of motion for the two particles. Okay. Now, as I said, I'm sort of going through this as an example to show you exactly where it's coming from. Ideally, when you get used to it, you'll just draw the one diagram out and just kind of be able to block everything out and say, right, well, that's T minus 2mg equals 2ma. And this one is 3mg minus T will equal 3ma. You can just write them down straight away. Okay. If you're never sure of what to do in a connected particles question, writing those things down at the start is always a good idea, because usually you'll be able to spot what to do next. Right, part B. Find the acceleration of each mass. Well, notice now that equation and that equation have a lot of the same variables in, don't they? Now, the only thing really throwing us here is the fact that the masses are given in terms of 2m and 3m. These things are simultaneous equations. They've got t's and a's and m's in them. Okay, so what we can do here is that we can look at these two things as simultaneous equations and use them to solve for quite a lot of the working out that we've got to do. So we'll write them down again. T minus 2mg equals 2ma, and 3mg minus T equals 3ma. Now, hopefully what you've spotted there is that I've got a positive 1T and I've got a negative 1T. And that means that if I add these things together, they're going to cancel, which are going to get rid of one of the variables for me. Okay? It's always add when you get to this stage, because one tension will be opposing motion and one tension will be going in the direction of motion. That means you'll always have one positive and one negative, so therefore we can always add these things together. So when we do, the t's will disappear, that 3mg will still be there, that minus 2mg will still be there, and 2ma add 3ma is going to be 5ma. Okay? So if we simplify that left hand side, 3 take away 2 means I'm going to be left with 1mg equals 5ma. I've got m's on both sides there, so I can cancel them. G will equal 5a, so g over 5 must equal the acceleration, and remember g is the number 9.8, so if we do 9.8 divided by 5, that gives me 1.96, so my acceleration is 1.96. Okay, very important that, because I can use that later on. So part C, find the tension in the string. Well, for part C, I now know what the acceleration is, so it means that I can figure out, I know what that is. Okay, so I'm now going to sub that into one of these first two equations to figure out T. So I'm going to write that equation out again. T minus 2mg equals 2 times m times 1.96. Okay, so T will equal 2 times 1.96m times 2, which is going to give me 3.92m, plus 2mg, which is 2 times 9.8, remember, 2 times 9.8, which is 19.6. So if we add them two things together, 19.6 add 3.92, and that gives me 23.52. Okay, you could have, if you wanted to, at that stage, and you can keep this in terms of G. I actually think it does in terms of the solution bank and everything. So that will end up being, it's the same as 12 over 5 mg, Okay, just check that if it's 12 divided by 5 is that, times 8 equals, yeah, okay. So if you're looking this up in the textbook or anything, just to check that I've got things right, that is the same as 12 over 5 mg. That's what it's called in the textbook. So that is the tension in the string. Okay, so every T in the diagram represents that. So now what we can look at is part D. Find the force exerted on the pulley by the string. Now, if I consider just the pulley, what acts on it? Well, I've just got two arrows acting on it, and both represent tension, don't they? So all I need to do there is do 2 times T, which is 2 times 23.52. So 23.52 times 2 will give me 47.04. Okay. Right, part E. Find the distance moved by Q, which is this one, in the first 4 seconds. Hopefully you've spotted when I'm starting to talk about find the distance moved, first 4 seconds. You know, what are we talking about there? This is suvat, isn't it? So let's list out suvat. S is what we're trying to figure out. U, well, remember this thing was released from rest, so U is 0. V, I don't know. I do know what the acceleration is. The acceleration is 1.96, and I'm being asked about the first 4 seconds. So I want to figure out S, and I know U, A and T, so I'm going to be using S equals UT plus a half AT squared. So S will equal, remember with this one comes up a lot in connected particles, when U is 0, that term is going to disappear, that's 0 times T. So I'm just going to figure out this term, a half times 1.96 times 4 squared, and that gives me that it's travelled 15.7 metres. Okay. Right, and part F, state how you've used the fact that the pulley is smooth in your calculations. Well, what did we say about the pulley being smooth? We said that if the pulley was smooth, it means there's no friction, and if there's no friction, it means the tension is the same. So we put no friction, therefore tension is the same throughout the string. Okay, right, what I'd like you to do is, there are 2 types of these questions really. One's like this and then one with a different type of diagram. So can you have a go at questions 1, 2 and 3 on exercise 10F? Sorry, exercise 10F. So try question 1, question 2 and question 3 please on exercise 10F. And then come back, so pause the video, have a go at 1, 2 and 3, check your working out, and then come back and we'll do example 14 next. Okay, so pause the video, go and do them, check your work using the solution bank, and then come back in a sec. Okay. Right, hopefully you were alright with those, so now we'll have a little look at example 14. So this time, 2 particles A and B of masses 0.4 kilograms and 0.8 kilograms respectively are connected by a light inextensible string. Particle A lies on a rough horizontal table 4.5 meters from a small smooth pulley which is fixed at the end of the table. The string passes over the pulley and B hangs freely with the string taut 0.5 meters above the horizontal ground. Frictional force of magnitude 0.08 G opposes the motion of particle A. The system is released from rest. Now, before we kind of get onto there, let's stop at this point and let's draw that diagram out. Okay, so 2 particles A and B, 0.4, 0.8. A lies on a rough horizontal table. So let's draw that out. Okay, there's particle A, rough horizontal table, and it's connected by a string, passes over a pulley, and particle B hangs freely down there. So this one is A, which is 0.4 kilograms, and this one is B, which is 0.8 kilograms. So You've got your weight acting down there, which would be 0.4 G. You've got your weight acting down there, which will be 0.8 G. Now, let's think about tension. Tension will act away from the mass, so tension acts there, and it acts there, like it did on the previous one. But in terms of this, tension will be pulling this way, and it will be opposing there, away from the pulley again. Okay? And the only other force that we need to put on there is the frictional force, which acts only on this one. So that is a frictional force there of 0.08 G. Okay? Now, in terms of direction, when this thing is released, this will move down. This will move to the right, it will go that way. Okay, so again, we can't look at this as one whole system because the things are moving in opposite directions and in different directions like that. So we'll again need to kind of consider each part. So part A, actually sorry, I've got some thingies to put on this, haven't I? Where am I? Particle A lies on a rough slot table 4.5 metres, so this distance from there to there is 4.5 metres, and this is 0.5 metres above the ground. So that's everything on there on that diagram. So part A, find the acceleration of the system. Well, how do we find the acceleration before? The acceleration, remember, comes from using force equals mass times acceleration. For both of these, they give us simultaneous equations that we can then solve. So let's consider particle A first. So particle A is moving this way. So in terms of F equals ma, tension, we're pulling it in the direction of motion, and friction, which is that number there, will be opposing it. So we've got T minus 0.08 G will equal the mass times the acceleration, which is 0.4 A. Okay? Considering particle B, let's look at particle B. This is moving down. What's pulling it down? The weight. So that's 0.8 G. What's opposing it moving down? Or tension, which is pulling up, so that'll be minus T, equals the mass times acceleration. Okay, again, hopefully there you can spot, well, I've got a positive 1T there, and I've got a negative 1T there. So what do? I'm going to add these equations together. So T add minus T will disappear. 0.8 G minus 0.08 G will give me 0.72 G, and that will equal 1.2 A. So I'm going to do 0.72 G divided by 1.2. So remember that G is not a letter, it's not a variable, it's 9.8. So 0.72 times 9.8 equals that, divided by 1.2, and we get an answer there for our acceleration of what's that, 0.6 G or 5.88. Okay. Yeah. So the acceleration there is 5.88. Right, part B. Find the time taken for B to reach the ground. Now, time taken for B to reach the ground. Time means that we're now looking at SUVAT, doesn't it? So let's draw out our SUVAT. S, we know, is going to be 0.5. U, it's released from rest, so that is 0. V, we don't know. We do know the acceleration is 5.88, and we want to figure out T. We want to know how long it takes for it to reach the ground. So we want these ones. Okay. So SU, A and T, we're going to be using S equals UT plus a half AT squared again. So we're going to get 0.5 equals UT, which is going to be 0 times T, so that is going to disappear again, plus a half times A, which is 5.88 times T squared. So I need to do a half times 5.88, 0.5 divided by that. What I'm going to do is 0.5 divided by a half, 0.5 times 5.88 gives me that, and that's T squared. So 25 over 147 equals T squared. So T will equal the square root of that. The square root of answer, that gives me 0.41 seconds. Okay, so it takes 0.41 seconds for this thing to hit the floor. Right, part C. And part C is quite tricky, okay? They ask this quite a lot, so these type of questions come up quite a bit. Part C says, find the total distance travelled by A before it comes to rest. Now, there are two parts to this journey. At the time B hits the floor, this thing will still be moving. So if you think about it, as these things start like that, that hits the floor there. And at that stage, what happens to the string? Because as this hits the floor, while these two things are both moving, the string is taut. Now when it's taut, tension is happening in the string. But as this hits the floor, the string loses its tension. So at that stage, it then starts to decelerate along here. So this thing will move a certain amount of time. It will move for 0.41 seconds using the acceleration that we've calculated here. It will then, though, change its acceleration because it will then start to slow down. Because as this one hits the floor, this one will continue moving until it slows down somewhere over here. Okay, so we need to look at two things. We need to figure out what the speed is when this thing hits the floor. So we need to figure out V there. And then we can use that V, figure out what the acceleration will be, the deceleration, sorry, and then we can use suvat again to figure out how far it will travel under that deceleration. So let's figure out the velocity when B hits the floor. So we've got quite a lot of information about this journey already. So 0.5, we know that U equals 0, V is what we want to figure out. We know A was 5.88, and we know T was 0.41. So we can actually pick basically loads of different equations to use here. If I want to know V, I'm going to use U, A and T, because I know the first formula that we ever learned in this was V equals U plus AT. Okay, so V will equal U, which is 0, plus A, which is 5.88, times 0.41. So that will give me, calculate it, sorry. That will give me around about 2.41. Just check I got that one right. Yeah, V equals 2.4. So V equals 2.4 meters per second. Okay, so that is the speed of this thing as this hits the floor. We now need to consider what happens after that. Well, in terms of this equation, when this hits the floor, tension disappears because the string then becomes slack, so there's no tension involved in the string anyway. So it gives me a new equation of motion. It gives me minus 0.08 G will equal 0.4A. Tension becomes 0 because the string is slack. That is what that becomes. Okay, so if I now solve this, if I do minus 0.08 times 9.8 divided by 0.4, that gives me a new deceleration or an acceleration of minus 1.96. Okay, so I can now use suvat again for the second part of the journey. Okay, so I'm going to do that over here. S is what I'm trying to figure out. U is this new speed here that I figured out, because if you think about it, that when you get to there, when B is hitting the floor, that's the speed. 2.4 is the speed of the system at that point, so that becomes the initial velocity for the next part of the journey. So that becomes 2.4. This thing is going to come to rest, which is what it says in the question, so that means that V is 0, A is minus 1.96, and I want to know how far it's travelling. So I want S, and I know U, V and A. Okay, so again we need to think about which formula we're going to be using. Well, that's V squared equals U squared plus 2AS, isn't it? V squared equals U squared plus 2AS. So 0 squared will equal 2.4 squared plus 2 times minus 1.96 S. So let's figure all that out. 2.4 squared is 5.76. 2 times minus 1.98, 1.96, sorry, gives you minus 3.92, which I'm going to take over to the other side. It's going to be 3.92s equals 5.76. So if I do 5.76 divided by 3.92, that gives me an answer there of around about s equals 1.5 meters. Okay, so what I've figured out here is that when the string goes slack, A continues to move for 1.5 meters. So to figure out the total distance it travels, I need to add on how far it travelled before that, which was 0.5 meters, to this, which means a total distance of 2 meters travelled. Okay, right, go back to the exercise then and try that last question for us, please. Okay, so question, where are we? Question 4 and 5, please. Okay, and then that's you done for your forces and motion.